All right, let's get started. Vicky has a very full presentation. So Vicky's got her undergraduate degree in Thessaloniki, I believe, yeah, right? And then got a PhD with Ronald Rebick in Illinois. Went to CFA, sort of 2 postdocs, and then was hired at Northwestern, where she helped create CITA, one of our rival organizations. And she's been working a lot, originally in mostly neutron stars, compact X-ray sources and so forth, but a lot more recently in the LIGO thing. So that's what she's going to talk about today. So go ahead.
Thanks, Norm. Hi, everyone. Thanks for coming. Thanks for inviting me. I feel like I need to start with an apology because I know it's been many years that every year there's a discussion about me visiting, and every year I can't figure out my dates. So finally I made it. And of course, I'm exceptionally happy to be talking about a LIGO discovery instead of giving my usual, up until 6 months ago, LIGO talk where we made a lot of predictions, and I've always said, we will, one day we will. I know, of course, you have a LIGO group here, and I've been in contact with Kip Cannon, who gave a talk, and I'm going to try and avoid as much possible overlap with his story, but I still have to cover some of the basics and build up a coherent story here. So let me get started by mentioning the fact that this discovery comes at the end, or it's really a beginning of the future, but the discovery comes after many decades of an effort by many, many people. But I have to acknowledge the fact that really the discovery comes as the result of perseverance, stamina, trust, commitment, whatever you want, whatever other kind of word you want to add, by a few key people who started in the 70s thinking about laser interferometry and how that might be the way to one day detect gravitational waves. So Ray Weiss, Ron Driver, and Kip Thorne were right there in the beginning, and they worked very hard to actually convince the NSF to provide them at first small funding, eventually make LIGO an actual national level project in the US. Went through another decade. I joined somewhere here around 99 as a postdoc at the CFA. So Harvard had the LIGO group for 6 months before I moved to Northwestern. And then we reached initial LIGO design sensitivity in 2006. I'll come back to that in a minute. And 2010, we finished initial LIGO operations, and it took about 5 years for a major upgrade of the detectors to get completed. And we turned on our detectors in September, end of August of 2015. And of course, we were surprised as much as everybody else. I'm giving this talk on behalf of a very large collaboration, as you can see. CITA, looks much better on my on my screen. Yes, and you can see CITA is actually at the center of this collaboration. And it's obviously a major challenge to work in a big collaboration like this, but of course nothing, detection like this in the beginning of a new era could not have started without the contributions of many hundreds of scientists and engineers making this possible. So in terms of my LIGO team basically at Northwestern, so I've been a member for almost 16, 17 years now. For the first half of that time, my focus, and this is my background, was on astrophysics. So modeling compact objects, populations, and also studying observed binary pulsars, trying to figure out what LIGO might see one day and how to interpret any observations. But really, our focus at Northwestern in the past 7 or 8 years has been on LIGO data analysis. So I became a proud data analyst, hoping for a detection one day. But mainly on figuring out how to best extract physical properties out of a potentially detected signal, and how to characterize the data in order to get the most accurate parameter measurements. So method development, applied math, statistics, data analytics was a lot of our focus for the past 6 to 7 years. And I wouldn't be a member of this collaboration without, of course, my group members. So I want to, this is a snapshot of some people, not all the people over the years, a couple of postdocs who now have moved on to faculty, current postdocs, graduate students who have moved on, current graduate students, and tons of undergraduates that I don't have the pictures of all of them, but tens and tens of undergraduates almost every year. Let's go back to the detectors. You all know there are 2 LIGO detectors. Initial LIGO really started operation in 2001, but it took many years. When you first turn on after a major detector construction phase, your detector is not working at the target sensitivity. So it took 5 years for the collaboration to basically build down the noise curve, build up the sensitivity until we reached design sensitivity in 2006. And then we had 4 years of operations to a level that exceeded even design sensitivity. But there was no detection consistent with all predictions. Some of the most optimistic predictions might have given you a detection in the late years there, but it didn't happen. So where are we now? Let me give you another sense of the future timeline. So we are now in the era of advanced LIGO, and advanced LIGO, just like initial LIGO, was planned as a staged project. So the plan originally, and this is a slide that was created well before operation started, was to have a 3-month run in 2015, and then progress in increasing longer and longer runs until about 2018 or 19 or 20, we might reach design sensitivity. One way we measure the detector sensitivity is how far away can we see in gravitational waves a double neutron star in spiral and merger. So in this metric, here's how the expectation is for the sensitivity to grow. Here we are, 2015. We were expecting to have in this measure a sensitivity between 40 and 80 megaparsecs. I should say the best sensitivity for initial LIGO for double neutron stars was around 20 megaparsecs consistently. So we were expecting at least a factor of 2 improvement. And when we turned on, we were up here consistently for our first observing run, so on the optimistic side. And then the plan is, right now the detectors are not working. They're down and being worked on by our instrumentation scientists. But eventually we want to, oops, I keep pressing wrong. OK, there we are. We expect to eventually be 10 times more sensitive than initial LIGO in this metric of double neutron stars. And of course, Virgo is expected to join us along the way. They're a little bit delayed, so probably they're going to join us in the 3rd observing run before we get to design sensitivity. Now, I'll be very unfair to our instrument and engineer collaborators who basically have to be thanked for any of us data analysts being able to stand and talk about the discovery. Because without the right detector, with the right sensitivity, we would not be talking about observations. So I'll tell you very, very quickly in one slide that what happened in the 5 years after initial LIGO was that we increased increased the laser power, bigger mirror masses at the end of the L-shaped interferometer were installed, better mirror coatings that improved thermal noise, and much, much more improved seismic isolation. Now, any one of those was years worth of work. So for example, installing a higher laser power messed up the detector big way. So you had to work and learn how to accommodate the higher laser power in the cavities, et cetera. So that's why it took 5 years. And when we turned on in September, this is another way of looking at the sensitivity of the instrument. You can think of this as a power spectrum, except it's not power that we measure. It's actually this amplitude of the gravitational wave that we try to measure as a function of frequency. And you can see the kind of step that happened. The faint lines here are the two detectors at the very end, 2010, of our initial LIGO operations. And when we turned on end of summer 2015, we were basically a factor of 3 more sensitive at the higher frequencies and a huge factor more sensitive at the lower frequencies because of the seismic isolation. It was this big jump in sensitivity that enabled this first discovery. So on that ordinary Monday of September, yes?
So yeah, the beach is Hanford.
Yes, so Hanford and Livingston.
So Hanford has more seismic nodes, or what's the deal?
The red curve less, yes. So they keep working. Of course, the configuration is identical in principle, but each side has its own quirks, and they're not always at exactly the same sensitivity. Okay? And you can see this kind of difference already in initial LIGO. They were not one on top of the other. Okay, so on that ordinary Monday, as I say, September 14, at 6 a.m. Eastern time, your time, the following happened. An automated email from an automated system that analyzed data online was sent to 3 people, Florida, MIT, and Germany. The only person awake was the guy in Germany, of course. And so he got this alert, which was not expected because our thresholds were very high. So he went and looked, and he saw, this is a fancy version of what he saw here, but he basically saw a banana like this in this plane of frequency plotted as a function of time. And what he saw is that, well, darn, this looks like a chirp. Increasing frequency from a binary spiral, increasing frequency as a function of time, and the amplitude is increasing where you see the white intensity there. So we know now, because we've talked to Marco, that he saw this and he thought something must be horribly wrong. What have I done? Not that he had direct connection to the detectors. So apparently he walked to the office next door with another postdoc from LIGO and said, come and see this. Do you see the same thing? What are we supposed to do? So eventually, the East Coast woke up. Actually, already within Europe, emails started circulating. So 7 a.m. Eastern time, an actual human email was sent that said, there's a very interesting event in the last hour. 20 minutes later, somebody said there was no scheduled hardware injection. We tend to inject signals to test our own pipelines. There was nothing scheduled for a hardware injection. Somebody else says 10 minutes later, very interesting indeed. It looks like a high mass in spiral. Then the omega scans, these time frequency plots I showed you, had completed fully and were reproduced. And somebody else that looked at them said, sorry, there we are, said, I do not see any data quality issues. This is continuous monitoring of whether we are in science mode and the data quality is appropriate. The data looks quite clean at both detectors. 15 minutes later, this is clean. It's very significant in spiral. We knew already with a chirp mass 27 plus or minus 2. We now know it was 29 solar masses plus or minus something. And the false alarm rate is less than 10 to the minus 10 hertz at this very fast, quick calculation. If this is not an injection, I guess we need to do the detection checklist. And what this meant is that we were preparing to come online officially, and we had set up a detection checklist with 173 items that I got to know intimately because I ended up serving on the detection committee that had not been formed yet. And you had to check a gazillion of things, and everything could take from hours to days to many weeks. Okay, and different teams inside the collaboration had to do their part independently and then bring together the information. So within a couple of hours, basically, we knew there was something very unusual and it looked like a massive in spiral. it took different people different amounts of time to believe that this was actually real. It took me about a month. But obviously the collaboration is now perfectly convinced that this was real. And back on that day, we went on a very unexpected ride because nobody was expecting a detection, especially at signal-to-noise ratio of 20. And the peak strain, those who have a sense of these numbers, was 10 to the minus 21. What does this mean? That the displacement due to the gravitation, the displacement of the mirrors at the end of the Michelson interferometer arms, due to the gravitational wave, the amplitude was 1 part in 10 to the 21 change in position. And this is what was measured. This, by the way, is now the most accurate measurement made by humans ever in any field in science and engineering. This is the signal now shown in a different way. Straight strain. You can see that the peak up there is 10 to minus 21. And on top of that, you see numerical relativity waveforms that have been affected by the residual noise we have in that frequency band. And I believe these were first produced, I think, especially the ones we're using for the publicity material were produced by Harold's group here. And the SXS collaboration. You can also shift the data between the two detectors because, of course, there is a light travel difference between the two detectors of about 10 milliseconds, depending on the orientation of the source. So the signal came from the south. It hit the Livingston detector, and then 7 milliseconds later hit the Hanford detector. And the data align perfectly well if you do that time shift. This is another way of looking at the signal, and I want to highlight one particular point here. This is my graduate student did this plot, so that's another reason I like to show it. Okay, gray is the actual data after you remove the broadband noise of the instrument as a function of frequency. And what you see in color is two things. The dark blue is the best fit to the data if you assume nothing about a binary in spiral. And you try to fit the data with just an arbitrary collection of signed Gaussians. No knowledge that you're looking for a binary in spiral signal. And the width of the line is actually the uncertainty in that fit at 90%. And then on top of that, you see what you get, thinner lines, light cyan. Excellent agreement. If you assume now you are looking for a binary in spiral, and you recover it in the data. And the point I want to make that is very significant is that you don't need to assume you're looking for a binary in spiral to find this signal in the data. You can find it with a generic burst kind of analysis. And the agreement is just remarkable. And the properties you extract are actually very much consistent from either analysis.
So for the wavelet analysis, you went down to some level in the wavelets. So was there signal-to-noise filtering, or was it just done by wavelets and getting rid of the high frequency by truncating the data?
So this is whitened data. So you don't have, it's not a bandpass filter, but effectively what you're doing is you are normalizing the data stream based on how much noise you have at different frequencies, and you're sort of cutting the low frequencies and the high frequencies. All right. Okay, I fear that I'm going very slow. This is everything we know about the source. Okay, that wiggle on the board gives us all this information. I'm going to highlight some of these, and I won't go through this table right here, but let me emphasize that the fundamental property for the signal that we measure is what we call the chirp mass, which is basically this particular combination of the two masses of the compact objects in spiraling and eventually merging. And they depend on the measurable quantities of frequency and frequency time derivative. The other thing I'd like to highlight is that this signal, it came in this early advanced LIGO run, and this is where our sensitivity was as a function of frequency. Blue is what we had as best sensitivity in initial LIGO. So if this signal had arrived then, and maybe signals like this arrived then, they were at SNR of 3, which is very deep into our noise. Basically, we need things to be above 10 or 12 to be considered high significant detections, okay? So we could never have seen this in initial LIGO. Once we go to design sensitivity, this exact same event will have a signal to noise ratio of 40 plus. This is very significant for tests of GR. So the higher the SNR and the longer the signal, will be doing better in testing GR. So on February 11th, we had the big press conference. I was in the room. It was an amazing experience. I still get goosebumps when I think about it. We released a number of papers. The discovery paper and the astrophysics paper that I was leading were both reviewed, peer-reviewed, and published. And then all the other papers, I think all but one now, have been published as well. And this is the long collection of papers. And of course, I won't have time to tell you about all the analysis presented in these papers. So I'll handpick a few key results, especially results where my group had something to do with. So this discovery came from analyzing 39 calendar days of LIGO observations. But in these 39 calendar days, only 16 days of coincident time was collected, because the duty cycle is about 50% in each detector, and of course it doesn't always coincide. The data were searched with 5 independent pipelines, 3 burst pipelines, which means no knowledge of binary in spiral, just burst generic waveforms, sine Gaussians, and 2 analyses where we assume we're looking for a binary coalescence. They all give the same consistent results within statistical errors. And the key analysis of what we do to extract the significance of the signal in the data is called time slides. So I'll try to describe it for those not in the LIGO collaboration in the audience. We take the data streams from the 2 detectors, and we shift them, time shift them in very small steps so many times, so we accumulate more than 200,000, the equivalent of more than 200,000 years of data. And for every time shift, we ask the question, what kind of disturbance appears to be coincident at what SNR? Okay? So this is qualitatively the basic logic, the algorithm of the analysis. And we have 5 different analyses, as I said, for different waveforms. I'm showing you here the results from one analysis. I should have picked the GST-LAL analysis, because this is more used here. But this is what I've had in my slides for the past few months. So what are we looking at here? X-axis is some kind of a detection statistic. I won't go into the details. You can think of it as signal-to-noise ratio. And then, through the time slides, you count how many signals appear in coincident. You get at different signal strengths. And then you do the same thing without any time slide, the actual data, okay, that we call the search result, and that's the orange points. And you normalize the number of events you get. You normalize it at, such that your loudest event is at 1. So you can see here that this event, which is the discovery, is sitting clearly orders of magnitude above the background. And in addition to that, if you remove this loudest event, you reduce the true background is this blue line. Why am I saying this? Well, if you leave the detection in the data, then as you do your time slides, you have this loud event in your data. So you get loud coincident triggers in your time slide fake data. So that gives you a high background. If you remove that little data segment, then this is the true background of true noise triggers or low significance triggers. All right, so here it is. Through this analysis, you can convert your statistics and eventually make a sigma statement, so greater than 5.1 sigma. But then you can see there's another couple of other things here. And this one is at 2 sigma. Clearly, you would never claim a detection at 2 sigma. But it's still above the background. And right now, basically, everybody kind of considers this an astrophysical source. But statistically, you can't exclude, there's about 14% probability that it could be noise. But if you analyze it, it looks like a binary black hole. All right, so physical parameter estimation. Again, multiple different ways of doing this, but fundamentally what we do is we assume a certain set of waveforms. They are all parametrized. They have lots of parameters, more than 10 parameters depending on the waveform. And we sample this high-dimensional parameter space with Markov chain Monte Carlo or other sampling techniques. We have 2 different samplers. We use 2 different binary coalescence waveforms and 1 generic burst-like waveform. And they all, in order to figure out which signal now in this very proper sampling of the dimensional space, high-dimensional space, which signal gives us the peak likelihood in correlation with the data. And they all give consistent results. And that's what allows us to basically make now physical measurements. Okay, you have the signal. Now you want to know what the source is. So you've seen these plots before. I won't expand too much on them. We can measure the 2 individual masses. Not great accuracy, but clearly we're at 30 to 40 solar masses for the more massive black hole, 25 to 30 plus for the second massive black hole. What we measure the best is the chirp mass, and this is the diagonal here on this plane. And the width of this ellipsoid is basically how well we can measure the chirp mass. The fact that the extent of the ellipsoid doesn't continue this way has to do with the fact that we can also constrain the mass ratio, and that truncates a little bit the extent of the ellipsoid. With these individual masses and from results from numerical relativity, we can actually also place constraints on the final mass, with the peak being around 62 solar masses, and the final spin of the black hole, which is about 0.7. And it turns out that 0.7 is what you get if 2 numerical relativity, if 2 non-spinning black holes come together in an orbit and merge. Okay, so this 0.7, 70% of the maximum possible spin of a black hole is really expected when you have no significant spin in the individual black holes. Talking about spins, we can also try and measure the spins. For this particular source, we can constrain the spin slightly. If we look at the spin components of the black holes, and we look at the component of the spin aligned with the orbital angular momentum axis versus this component of the spin perpendicular in the orbital plane. For the aligned component, we can set a tight upper limit of its magnitude, but obviously it includes 0. And then for the in-plane spin component, really we cannot extract any constraint. It looks like maybe we have a peak here, but actually the green line, for those of you knowing something about statistic sampling and Bayesian analysis, the green line is our prior. So we recover our prior, basically. And the reason there is a peak there and it's not flat is because we assume spin orientations isotropic in space. So in this magnitude, in this representation, the prior has a peak. Okay? So this is limited spin information. Distance is important for electromagnetic observations. And we can constrain it, but not as well as astronomers might like. So around 400 megaparsecs, this is about 0.1 in redshift. And the reason we cannot constrain it very well is that distance is degenerate. How far away your source is degenerate with how the binary is oriented with respect to our detectors. And this degeneracy gives you this V shape here. And you can see that basically when you project it on the distance axis, you don't get as good a distance determination. One thing we can say is that this binary is probably face off, okay? Because you have a preference for face off versus face on, meaning the orbital angular momentum axis were actually pointing away from us. This is what we saw in the sky. The first time I gave this talk to the public and I showed this one, somebody later came and said the sky is smiling at you. And I love that thought, so I keep it in my mind, except we would love as astronomers to have a smaller smile on the sky and localize the source a little better down the road. Okay, so quick note about electromagnetic, yes?
Has anyone studied yet how well it would have been localized if Virgo had been running?
I think the next slide. Okay. So this shows you, again, the localization, the black lines on the sky in a different sky configuration, and then each tile at different colors is all the electromagnetic observations that happened hours and days and tens of days after the discovery was shared with our electromagnetic partners. So X-rays, optical, infrared, and radio was followed up by different instruments, different groups. They all reported upper limits, except there is a potential Fermi gamma ray burst counterpart, question mark. The paper is not accepted yet. When the rumor came out that Fermi may have a counterpart, it was surprising because two black holes without matter, you don't expect electromagnetic emission, okay, if everything is clean. But that didn't prevent theorists from coming up with ways of actually, within days of the rumor of a Fermi counterpart, put up, several theories put up ideas for how a binary black hole might actually produce an electromagnetic signal, and I will not expand into these ideas. I will, though, point out for my colleagues who know Avi Loeb, is that notice that the other two are also Avi's ex-students. So it is the culture of going after the rumor and coming up with a new idea. All right, many people have expressed doubts about either whether the Fermi source is an actual source or whether some of these suggestions are actually realistic or not. So there's plenty of debate, which we love in astronomy. And we'll see where that goes. But most of the people right now don't think there was a gamma ray burst counterpart. We're about to get to your question. All right, so this is the big smile that we got. The little dots there is what you would have gotten if you had Virgo, and then if you also had India down the road. And here's the expansion, so you can see the blue contours of the big smile. And this is how much better you would have gotten it, okay? So yes, it will make a big difference. Another way, now this is one particular signal. We would go down from hundreds of degrees down to about 10 or less square degrees on the sky. A few years back, before advanced LIGO came out, we did a more systematic study for a double neutron star in spiral, high SNR assumption. If you have the 3 detectors at design sensitivity, so this is now looking towards 2020, then the median error box on the sky would be 10 square degrees. Much better than the hundreds of square degrees we have now. If you add India, all the little blobs become red, which is basically about 5 square degrees, the median. Okay, so it will improve. It will never be arc minutes, okay, unless suddenly unless we get LIGO Australia and LIGO India. All right, so let me just take half a minute maybe to highlight the following. This is the discovery announced at 5 sigma. Time, false alarm rate, the final answer from all the detailed offline analysis, statistical significance. Chirp mass, it's 28 plus or minus 2. Individual masses, this is something about the spin, and the distance I showed you. Compare these to that second 2 sigma trigger in the data. And if you assume it's astrophysical, and then you go into the same analysis to extract physical parameters from that signal, it's a 2 sigma signal, as we said. False alarm rate is 1 per half a year. You know, that's too high for a claim. But here's the black hole masses if this is an astrophysical signal. About half the chirp mass and about 2.5 or so further away. SNR was, I think, 9.6, 9.5, depending on the analysis. So you can't claim it as a detection. But the second trigger contributes to our analyzing the data and extracting rates. And where is Heather? I know one of your graduate students here from physics has worked on exactly this analysis. And although the plots were made by a postdoc at Northwestern, obviously that's the meaning of a collaboration. So what do we have here? You can assume you only have GW150914, and with a false alarm rate and everything, calculate that there is a probability distribution function for the potential underlying rate for the black hole, assuming all binary black holes are like this one, okay, which is an extreme assumption, of course. Then if you do the same thing with the other trigger, which we do not call a GW event, then you get the red curve, and then the combined is the blue curve, which obviously is dominated by the red curve. And the reason is that the second 2 sigma event is, which came in October, is much weaker, lower masses, so we can't see it as far away. So that means you have a lot more volume out there, a lot more of these signals. So actually, the weak signals dominate the rate calculation. Now, if you move away from the properties of these two, and then you assume some broadband binary black hole mass distribution of 2 different models, you can see the systematic variation in the rate prediction. Punchline, the rates now are not well constrained. Well, of course, we have 1.5 events, okay? So we have a couple of orders of magnitude in rate predictions. I certainly knew that very well when I was studying double neutron stars and extracting rates. But the one thing we can tell firmly, because actually the lower limit is the most significant part here and better determined, is that low rates, rate predictions below about 1 per cubic gigaparsec per year, which is our standard rate density units, are excluded. So the low rate predictions are now excluded for binary black holes. All right, how much time do I have for the astrophysics? Oh, not too bad. Okay, all right. So I'd like now to discuss astrophysical implications of this one discovery. And it's not clear, with one event, it's not clear you could have any astrophysical implications. But this one event had some particular characteristics that have been a little useful. Well, first of all, it's the first time we now know observationally in gravitational wave astronomy that binary black holes exist. We didn't know that. Okay, it was predicted, everybody expected it, double neutron stars exist, double black holes should exist, but really, it's the first actual observation. The second significant thing is that the black holes we're measuring from this one source are what I would call heavy. Please use the term. They're not massive, because massive is in the galaxies, right? So we were struggling with what word to find in our paper. So we call them heavy stellar mass black holes. And they're heavy compared to what? They're heavy compared to the black hole masses that we measure in X-ray astrophysics from X-ray binaries, where we track the motion of the binary companion to a black hole, and we can figure out and constrain the mass of the black hole. All those masses are no more than, even with the upper end of errors, they're no more than 25 solar masses. Now we have a 35 solar mass black hole. You might say, 10 solar masses, it's astrophysics, who cares? But it does have a little bit of an implication. And the reason is that given our understanding of how massive stars evolve, which is far from well understood, but given our current understanding, you cannot form in solar metallicity, the metallicity of our galaxy, broadly speaking, you cannot form black holes more massive than, in this particular model prediction, more massive than about 15 solar masses. Okay, this weak wind curve is basically our current understanding for how wind mass loss affects massive stars. And you can see that our current understanding tells us that I can get more massive black holes. This is black hole mass maximum you could form at a given metallicity. You can form more massive black holes if only you had lower metallicity. Now, before 2010 or 2028 or so, we thought the winds corresponded to this dotted curve. So back then, we could not form massive black holes more than 25 solar masses at any metallicity. Okay? So stellar astrophysics understanding of massive stars has improved, and now we think we live in this world. So that means that you can take the black hole mass measurements from the event. Here they are, blue and pink, and say, what's the minimum metallicity I need to form the low end of the massive black hole? And in this particular set of models, you would need to be at, I don't know, 1/3 of solar there, okay? But these are not the only models out there, and massive stars are not as well understood as we would like. So other groups have presented models in the recent literature. This was before the detection, by the way. Where you can see that maybe you can have a little bit higher metallicity, and I won't describe all the curves here. But basically, in this set of models, you can form the massive black holes we're observing, maybe if you have half solar. But beyond half solar, there's no prediction out there that we can form these massive black holes from stars. So a very conservative limit we are setting as a collaboration is that the population that form these binary black holes that we're observing must be coming from subsolar environments. Now, how do you form binary black holes? Well, that's what I worked on for many years when we were waiting for detections. And it turns out there were tons of theoretical predictions. I'll give you a snapshot of the literature evolution for how binary black holes from stars can form. And they can form in two main, very different ways. You can take binary stars, regular stars, massive, in isolation. They'll go through their evolution. Each star will form a black hole. And if the binary does not get disrupted, then you might get a binary black hole that is tight enough that eventually it will merge within a Hubble time. You can have this binary black hole formation from isolated binaries at low metallicities. People have predicted it all the way back to POP3. Or you can do it through a different kind of detailed channel by involving very rapidly rotating massive stars that avoids a lot of the messiness of the evolution of these binaries. A completely different way is to do it in dense stellar environments where you have stars in dense clusters, you form black holes, they sink in the center of the cluster, they start dynamically interacting with one another, forming dynamical binaries, kicking themselves out of the cluster, eventually forming tight enough binaries for them to merge within a Hubble time. So I want to give you a snapshot of literature, starting first with the isolated binaries for a couple of reasons. First, I want to point out that the very first mention, to our knowledge, the very first mention of binary black holes, not merging necessarily, was in 1973. You have to realize this is before the double neutron star was observed. We didn't know double compact objects could exist. And it was predicted by Sasha Tutukov and Lev Yugelson back in 73. The article actually exists only in Russian, but we have Russian members in our collaboration. So we tracked down the paper, and we had a couple of people translate it independently. But really, and this was a sort of very qualitative sort of, I wouldn't even call it a calculation and a prediction. But in the late 90s is when the real quantitative modeling of binary evolution started, and people started discussing binary black holes. That's about...
There was an 84 paper by Bernard Carr and I, in which it was all about the...
But did you talk about the evolution? So we wanted...
Yes, we did, actually.
Okay.
But not in absolute detail, but just relating it to the binary population. And there was a whole sequence...
And mentioning binary black holes?
It was all about, it was in the title.
Oh my goodness, we missed that.
And there was a whole history.
Were you upset when we didn't refer to the paper when we published the astrophysical implications?
It is known in the LIGO collaboration that the paper exists. It's just that the population that we were envisaging was actually more related to the ability to extend the bars with the signal.
I see.
Fire.
Yes,
But
yes.
it was a sequence of papers, some out of JPL before that, from, in the late 70s. Esteban, is that the name? There were a few.
I don't know those papers.
And then ours, we think we did a very big analysis.
We need to talk.
I will give you one of the...
Absolutely, I will take it. All right, I guess I'll have to correct this slide. I can't correct the actual paper though, but in future papers. Okay, so I entered this era somewhere here. No, actually for binary, I was studying neutron stars for a long time. The first paper I was involved with was actually in 2002 with my then student Chris Belczynski, and then a few other papers from my group. The second point I wanted to make is that people after the discovery said, oh my goodness, these black holes are so massive. Nobody has ever predicted these massive black holes in binaries. And I just want to say, no, that's not quite true. And that basically heavy binary black holes were predicted starting with Chris Belczynski in 2010 and followed by other groups independently. And the reason was, there were two reasons for how now the predictions evolved into heavier black holes. One was these weakened stellar winds I mentioned earlier. The other was that for the longest time, all these papers are all about the Milky Way. What does the Milky Way form, okay? And people started doing simulations for various star formation environments and realizing that at lower metallicity, you're getting, of course, heavier black holes. Okay, I'll have a quick flash without describing it of how, just to give you a sense of the fact that it's rather complicated and there's a lot we don't understand in terms of how these things form. This is an isolated binary that has to go through many phases, many of them we don't understand quantitatively, and potentially form a binary black hole. But the punchline I want to make is that right now, with this one source, we cannot distinguish between different formation channels. So this class of predictions, regular stars I call them, in binaries, they predict both masses and rates consistent with the observation. If you go to the very rapidly rapidly rotating stars model predictions that really came out very recently, like actually the first paper came out after the detection, but before it was public. You can avoid a lot of the complications of regular binary evolution. Maybe this is forming binary black holes. Currently, the masses and the rates are consistent. I will point out that this channel cannot form low mass black holes, okay, because of the rapid rotation. So if we eventually have detections at lower and lower black hole masses, we'll be able to distinguish things. Now, tell me what papers I missed in the stellar dynamics history of the evolution. So I just want to say that people started studying clusters and binary black hole formation with point mass black hole dynamics alone back in early 90s. Then good binary evolution, Mickey Mouse dynamics, a few papers. Actually, all of these were Fred's group at Northwestern. Good dynamics and binary evolution really started 2010, partly for computational challenges that were not faced any before. You might recognize Fabio's name here. All of these, all but the first two are actually Northwestern work. So galactic centers have been discussed by other groups and young star clusters by other groups.
So there was a whole history, in fact,
before the 90s. But
huge industry of black holes and globular clusters, as you probably know.
But the first, well, in terms of form, so black holes and globular clusters, yes. But we're looking at papers that discuss binaries formation that will merge. And that's where I think the first mention of actual individual black holes in dense clusters forming binaries was actually Stein's paper with Lars.
I'm thinking
That's what, but you know, I could be wrong.
Well, the point was that you would get a situation, I mean, this is the big problem with globular clusters in the interiors, that you would get a situation where you would have three things and one
Yes.
goes away and then it gets closer together.
Yeah.
And so that was all And that was, all the way through the 80s. It was
Okay.
really what was the dominant activity for cooperative cluster
Okay.
research by dynamicists.
I remember, so even Stein's paper doesn't have, in terms of binary black holes, but we can talk offline, okay? Doesn't have references to earlier as far as I remember. That again is just pointing out from recent simulations that black holes in clusters can go through a gazillion of different types of exchanges and hardenings of binaries, etc. And eventually you can get binary black holes that have the right masses and the right rates. Again, if you see though the predictions, total binary mass, current predictions don't give you total binary mass below about 20 solar masses. And this is work by Carlo Rodriguez, who just graduated from Northwestern. All right, punchlines on the astrophysics. Okay, I will not repeat them, just very, very quickly. They exist in merging binaries. This event must be coming from subsolar environments in terms of metallicity. They can form through all these channels that have been discussed in the literature. We cannot distinguish among formation channels. Low-end rate predictions are excluded. Yes?
Jen?
I haven't finished though.
Basic question about when you're forming the black hole and these binaries and centers of it. How much of the mass is coming from more than the helium? Is this basically helium core, or are you really?
At low metallicities, like in global cluster level metallicities, 10 to minus 3, you still have quite a bit of the hydrogen envelope. So whether the assumption in these models is that once you're above, I don't know, 50 solar mass or so, the whole thing becomes a black hole. Whether it's correct or not, really, we don't know.
Collapsing the hydrogen, it's hard to get slow rotation in the black hole.
Yes, that's true, but it doesn't mean they're all slowly rotating. And plus, we cannot constrain the spin in the plane, so maybe there is a high spin component there. Okay, now I'd like to make a couple of quick comments. I'm trying to debate what to do. Well, I'll tell you very quickly that there are hopes for distinguishing formation channels based on mass ratios and chirp masses. For different channels, you get clearly different predictions. Spin orientations, the tilts, the isolated binaries should give you aligned spins, really. The cluster dynamics should give you random spins. And then rate evolution as a function of redshift. If we can dream of having lots of events, then we can probe the rate as a function of redshift, and different model formation channels give you different predictions. Then I had a few slides trying to convince you that yes, this work could be done eventually because the models make different predictions. There's also a possibility of having the space-based mission detecting these heavy binary black holes. We're working now with a student at Northwestern. This one did not come out very well either, where we can see that eccentricity measurements in the Lisa band can tell you that things are coming from clusters versus from the field. So there's a lot of potential there. Down the years, up until we reach design sensitivity, we're going to be seeing these massive black holes further and further away, all the way out to redshift of 2+. We could even hope, yes?
Go back to that for a second.
Yep. Yeah.
Okay, so on that scale.
Yes.
that's
This scale, yes.
This is mass,
This is total mass.
and let's take the red line.
Okay.
Which is 2017, 2018.
Yes.
So, I mean, this comes to the issue of how the
Sensitivity curve, and that's basically the inverse of the sensitivity in many ways.
So I would have, okay, so I would have expected that what is really happening
Yes.
is that the yellow curve
Yes.
is actually down,
Yes.
and then it starts to rise up as you are able to push the noise.
To lower and lower noise levels, yeah.
My interest here is
Intermediate.
remnants that are above.
Well, that's the next slide, actually. So here it is. So, but it's only the design sensitivity plot I have for equal mass ratios and non-spinning black holes. with design sensitivity, we could see these kinds of intermediate mass black hole mergers all the way out to 15 or so gigaparsecs. And then you drop down.
So it's not bad.
Not bad at all, if they exist. And you drop down because basically you have these very high masses, they get off the LIGO band. Okay? So, okay. Let me see. One last point. Here's what we are expecting. We have finished O1. We haven't reported on the rest of the data. 39 days have been reported. We have 3 times more data. About 3 times more data, although the duty cycle was not great, so a little less than 3 times more data. If you take the median rate prediction right now, rate constraint, there is a 90+% probability that the rest of O1 will give us more than 0 detections. Okay, I'm used to talking about predictions. As we go to our second observing run, there is a very high probability that we might have more than 20 events. As we go to our observing run 3, still below design sensitivity, we're talking about 50 or 70 events. So there's a lot to look forward to. I don't know how we're going to analyze all of this and keep reporting. There's a lot more to be looking forward to with neutron stars. I won't have time to expand there. I'll stop here. Thank you.
So the plot you showed of the maximum black hole mass with the weak and strong winds, was that for the binary system or just?
Those particular plots were single stars. So
If you kept following that line of 0 metallicity,
So one reason, so let me go back to that plot very quickly. So one reason this is sort of the safety for single stars, because if it's clusters, then it's the single stars producing the black holes, okay? So in binaries, you can have binary interactions and you can reduce the mass. So here you can see more clearly. This is remnant mass as a function of the 0-age main sequence. If you're in binaries, it's easier even at lower metallicities to potentially lose some of this excess mass. So then you would not produce as massive black holes because you lost the envelope because of a binary interaction instead of stellar winds. But this is sort of the conservative best case scenario if you only look at single stars.
Yeah.
Was there any constraint placed on the eccentricity of the
We don't have eccentric waveforms that are for prime time, so we haven't done actual analysis. The only thing we can do is sort of track the phase evolution and put a weak constraint on the eccentricity. We can tell that it cannot have been more than 0.1. Because if it did, then we would have a phase evolution that could not be matched with what we saw. But that's a rather weak constraint. To place real constraints, you would need to have eccentric waveforms and do the proper data analysis.
You know how far away we are from measuring eccentric?
Prayush can tell you maybe, because he's working on that. Okay.
Okay, if that's all the questions, let's thank Vicky.
Okay, thank you.